Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on November 3rd, 2025, about 5 days ago. The main punchline is a NUMA-Aware scheduling strategy that keeps each attention head on a single chiplet, delivering up to 50% higher performance and sustaining L2 cache hit rates between 80 and 97% on modern multi-chip GPUs. The paper is titled, Optimizing Attention on GPUs by Exploiting GPU Architectural NUMA Effects. And as we'll see later, the implications for training and inference efficiency at long context and high head counts are quite significant. Alright, the previous segment set up the core idea. Figure 1 shows how GPU designs progress from a single die with one shared L2 and memory controller to multi-die chiplets with separate L2 caches and high bandwidth memory stacks. The dual and quad die layouts introduce non-uniform memory access because each die favors its own memory. NVIDIA tends to hide this with full cache coherency, whereas AMD exposes it, which enables software-level scheduling gains. Well, Figure 1 showed why chiplets create non-uniform memory access. Figure 2 illustrates how workgroup placement affects cache reuse across dies on an MI300X style design. When related tiles land on different dies, each private L2 cache cannot help the other, so both fetch the same data again through high bandwidth memory and the last level cache. Co-locating related work on one die preserves L2 reuse and cuts redundant traffic, which boosts throughput. Alright, the previous figure emphasized that co-locating related tiles preserves cache reuse. Figure 6 clarifies how that grouping works by defining an attention compute cluster, which is the set of workgroups that share the same K and V tensors, so their data can stay hot in one L2 cache. The left panel depicts multi-head attention, where each head owns distinct K and V, so there is one attention compute cluster per head. The right panel shows grouped query attention, where several heads share one K and V set, so a single attention compute cluster spans the whole group. So Figure 6 defined the attention compute cluster. Figure 10 shows how Swizzled Head-first Mapping assigns each attention head to a single chiplet. The 4 XCD boxes each host one head's row blocks and its L2, which keeps K and V data hot and avoids cross-chiplet traffic. The color coding indicates distinct heads, and the layout ensures one attention compute cluster per XCD at a time. This mapping scales cleanly for 8 heads across 4 XCDs. Okay, the previous figure mapped each attention head to one chiplet. Table 1 summarizes the MI300X hardware that makes this strategy pay off. The GPU has 8 XCD chiplets, with 38 compute units per chiplet and 64 stream processors per compute unit. Each compute unit has a 16 kilobyte L1 cache, and each chiplet has a 4 megabyte L2 cache, which totals 32 megabytes. High bandwidth memory provides 192 gigabytes at about 5.3 terabytes per second, so locality really matters. Alright, the previous table detailed the MI300X chiplet layout and cache sizes. Figure 13 shows L2 cache hit rates across batch sizes, sequence lengths, and head counts, and the trend is stark. Swizzled Head-first stays high, around 80 to 96% across all settings. Naive Head-first slides to roughly 40 to 60% at long contexts, while both block-first variants collapse toward single-digit hit rates at large heads and long sequences, which explains their performance losses. Alright, the previous figure showed L2 hit rates collapsing for block-first mappings at scale. Figure 12 reports performance normalized to Swizzled Head-first, and the pattern matches the cache story. Swizzled Head-first stays near 1 across batches and sequence lengths, while Naive Head-first drifts lower at long contexts. Both block-first variants drop sharply once head count reaches 64 or 128, and context hits 32K to 128K, which signals severe locality loss under load. Okay, 2 takeaways stand out. NUMA-Aware head-first scheduling that keeps each attention compute cluster on one chiplet sustains high L2 reuse, about 80 to 97%, and yields up to 50% higher throughput at long contexts and large head counts. The implication is clear. Spatially aware runtimes are essential on multi-die GPUs. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.